I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
For some reason, I expected you to say bonus edition, even though this is just a regular old edition.
Yeah, false alarm.
I think we're recording, I think we've mentioned a few times, we're recording significantly ahead.
Yeah. Because
Jam is preparing for paternity leave and I'm preparing for vacation.
Yeah.
To reward myself for getting a PhD.
Yeah.
So a pretty big, long-term vacation, like several weeks of being out of town.
We could probably come up with some term for something like something-itty leave. Maternity leave, paternity leave, PhD-itty leave.
Doctor-itty leave.
Yeah.
Yeah, it is kind of like I had a baby.
Yeah.
You know, it's like I put all this work and effort into keeping this thing alive for 5 years, but it's almost like after the the baby's.
Yeah.
Now it's the easier part, like the baby just turned 5 or something.
Right, where it's kind of the other way around with, it's like you're building up to the hardest period sometimes.
Yeah, when you're about to have the baby. Yeah. Like, I should have taken my doctorate leave during the 2 months where I was writing that dissertation.
Yeah.
That's when I needed my paternity leave for my dissertation.
Yeah.
Anyway, all that to say that we're way ahead and I don't know what's happening right now. But I'm happy to be here today because we're going to be talking about something that's in response to a listener question.
Nice.
This is from listener Wendy. And Wendy asked a specific question that I broadened out.
Okay.
So Wendy's question was, why does water expand when it freezes while many other things condense as they freeze?
Right.
So that's a good question, but I actually think a more everyday life question is then why does ice float on water?
Okay.
So we kind of touched on this a little bit when we did the snowflake episode.
Oh, yeah.
And we talked about the reason snowflake has their specific shape.
Right.
But I don't know if we talked about the implications of that for water as a solid versus water as a liquid and literally water floating.
Right. Right. And it's been of course, a ton of episodes that have gone into some differences of liquids and gases and solids and stuff. It's always been a principle, but it hasn't been the main thing of an episode in this way, I guess.
Right. Exactly. And I think that what is good about this topic is ice floating in water is very everyday, but also some other experiences that I think many of us have had are pretty everyday. Like, did you have the thing when you were a kid and you figured out you could freeze water to have really cold water during the summer because it was so hot in Texas? And then you got over ambitious and you froze a whole water bottle full and it exploded? Yes. You had this experience?
Uh-huh.
I thought it might be a universal kid experience.
It is. My version, I think the one that's more like memorable for me is when I tried to do that with a soda.
Yeah.
And it,
Uh-oh.
Yep.
Yes.
Caused a mess in the freezer.
Yes, definitely. And that is because water expands when it freezes, but that is not intuitive to us, I don't think.
Yeah.
Especially as children, because other things don't expand as they freeze for the most part.
Right.
There are only a few substances that expand as they freeze, and water is one of them.
Right.
So, and there's some cool implications for this in everyday life that I'm going to talk about at some fun facts at the end. But right now I want to talk about why this happens.
Okay.
And I also think this is a fun kind of a philosophical question because Galileo actually had a public debate. There's a Chemistry and Engineering News article about this. He had a public debate back in the day about how can ice float in water when ice itself is water. So this is literally an age-old question that we're doing. And it's cool because they didn't have the answer then, but we do have the answer now. Isn't that weird?
Yeah, that is crazy.
Okay, so the reason that it can float is literally just because it expands as it freezes. But that phenomenon is the weird part. So that's what we're going to actually focus in on is, I guess, you have your answer to the first part. If you just want to know why it floats, it's because it expands.
Right.
But now I'm going to tell you all about why it expands.
Okay.
And also sort of why other things don't. Okay, so let's just talk about what happens to molecules in different phases of water.
Okay.
And we've talked about this a lot before, but it's definitely always valuable to revisit. And it's also valuable as a student of chemistry for you to have in your mind the idea of what's going on at the molecular level. We've talked about this before, but this idea of understanding different representations of molecules is an important part of understanding chemistry, right? So
right.
In the chemistry education world, we call this representational competence. Are you competent in understanding different representations of a molecule?
Okay.
And I got so excited when we did the episode about why your tires go flat in the winter, because you demonstrated this ability to understand what was going on the molecular level. You knew that there were molecules in the tire. You knew that we put energy in and the molecules spread out, and that must put more pressure on the container. And I was like, oh my gosh, you got it. I was so excited. And so that's something I want to build into our listeners' minds as well. So that's why I always take time to revisit what's going on at the molecular level.
Right. Because at least like things we learn about the molecular level can be applied to other things too.
Yes.
In all kinds of different situations.
Exactly.
Yeah, makes sense.
You can use this to understand what's happening at the molecular level in everyday life, not just in this one situation.
Right.
So now imagine, if you will, I'm going to use a analogy. I'm going to steal your your job from you yet again this week. Sorry. I've been doing this a lot lately.
It's okay.
Thanks for forgiving me. So,
I mean, in some ways, I think it's good because, one, like I said before, helps me understand it better the first time, which is good for me, good for you, good for our listeners. Also, there are some times where the quick turnaround of coming up with an analogy in the moment is hard. And sometimes, especially these days, as we're recording a lot and fitting a lot in, preparing stuff like that, my brain, and right now we're recording late in the evening, the brain not always at its
not 100%
sharpest. So it could be that I would come up with some really weird, off the wall, not helpful, really dumb analogy, and you are saving me that embarrassment. So for that, I thank you.
That's true. Okay, well, so what I liked as an analogy for this part is actually a concert hall of some kind. So imagine like a band playing a concert. I've been into T-Swift and Lizzo lately. So imagine, someone on the stage who's really popular, and there are so many people there to see this show that they are jam-packed in this concert space.
Okay.
There's standing room only, literally. There's not a dance floor. There's not a mosh pit. Literally packed in shoulder to shoulder, as close as people can possibly get.
Okay, got it.
Okay, so, and the thing that's holding the atoms together when they're this jam-packed together, well, really always, are intermolecular forces.
Right.
Now, actually, let me say that again. Now, in molecules, the things that are holding the molecules together, like if you have a bunch of water molecules, or maybe a better example for this one would be something that gets smaller when it freezes, so a different type of molecule. The thing that's holding them together is intermolecular forces.
Right.
So that's your typical solid, is the molecules or the atoms, depending on what kind of substance you're looking at, are so closely jam-packed together that they aren't able to move very much.
Okay.
They have wiggle room, the molecules themselves are vibrating, shifting, whatever, but they're not walking around the concert hall. There's not a lot of movement happening. There's like slight movement within the individual molecules, but that's kind of it. They're sort of locked in.
Okay.
And oftentimes there's a strongly repeating pattern called a crystal structure. Not always, but the more well-defined that repeating pattern is, the more highly crystallized the substance looks. So that's why sometimes you get really beautiful solids, or you get really beautiful cubes of solids.
Right.
So typically solids are packed in really tight. There's not a lot of room for movement. Your intermolecular forces there's not enough energy to overcome the intermolecular forces to get the solid to spread out, the molecules inside the solid to spread out. And this is the solid state. Now, if you imagine having the same number of people in that same space, and you just make the room there in bigger, and you give them more room to spread out, that's more how a liquid moves. You'd have to put energy into the molecules to let them spread out,
right,
or relieve the pressure, either way.
Yeah.
But taking away that pressure, putting energy in, maybe give them some food, some drinks, get them excited, let them spread out a little. Let them dance, let them, move around the dance floor. We got room now. They're not just packed in. They get to enjoy the show a little bit more. That's kind of how a water molecular structure is, where it's still one group of molecules. They're still bound together through these intermolecular forces, but the intermolecular forces, there's enough energy in them that the intermolecular forces are starting to be overcome. The molecules can spread out a little bit more. They're not as jam-packed and closely together. So this is the equivalent of humans moving around the dance floor. They're individually moving, but they're also moving around within the room. There's just a lot more movement happening. And that's why typically the same number of molecules in a liquid takes up more space than that equivalent number of molecules in a solid.
Okay, got it.
So if you have two of the same number of things that weigh the same things and one takes up more space than the other, that thing is less dense. There's less weight per unit.
Right.
And so usually that thing will be the thing that floats.
Right.
So typically, if I have a liquid and I drop in the frozen version of that, that frozen version will sink because the molecules are packed so closely together that it's more dense.
Got it. Okay.
And
so
then,
would that be, what would be a good example? Like a metal or something like that? Like,
yeah, it's hard to come up with a good example because for most things, as soon as you start to drop that thing in the liquid version, then the molecules are going to start to get energy put into them and they'll start to melt. So it's hard for me to just be able to visualize off the top of my head a time where I've dropped a frozen thing into something else and it sank. Hang on. Let me think, and you listeners at home also take a minute and see if you can come up with a solid that sinks in the liquid version of itself. And I'll think of it too and see what we can come up with, because for some reason it's not just coming straight to my mind.
Yeah.
Okay, so we were sitting here trying to think of something, and my husband happens to be hanging out listening to us record. He doesn't have anything better to do on a Thursday night. And so it's kind of like he gets a live podcast. That's kind of fun.
Yeah.
Maybe we should do a live podcast for others. And he came up with this one that's really good, which is butter. When you melt butter, the liquid seems to sort of float up around the solid. The solid stays at the bottom.
Yeah.
Now I want to go melt some butter and drop some other butter in it and see if that really holds up. But I think that is a good representation.
Which might be true about other oils and that kind of stuff too.
Yes.
But yeah, the butter's the one that I think most people would have interacted with.
Yes. And that's the thing about this concept that's kind of weird is I think as non-scientists are like, oh yeah, water expands, so other things must expand, but other things don't expand.
Yeah.
As they freeze. Water's kind of the only one.
Okay,
so back to the analogy. We've got our solid stage where everyone is really packed in, and then if you can increase the volume, put a little bit more energy in, take away some of that pressure, people can move around a little bit more, and that's equivalent to the liquid state. And then the gaseous state, I really like this, is when everybody just goes home. They all spread out. They go wherever they want. There's tons of space in between everyone. They just leave. And you put energy into the car to get there, so it's even more energy. So there is effort in overcoming those intermolecular forces, but we're just spreading out, going everywhere we want. Boom, that's the end.
Yes.
So that's the gaseous stage.
Anywhere they can go, they do go.
Yes.
Okay.
Exactly.
Anywhere a gas molecule can go, it will go.
It will go.
They will spread out.
It tries to get out. Yes.
Yeah.
So here's what's different about water.
Okay.
It sort of follows that same structure in that the solid state is pretty fixed and it doesn't have a lot of energy for the molecules to be moving around freely, which is why it's solid and not liquid, right?
Right. And it is at a lower temperature.
It's at a lower temperature. It doesn't have the energy for those molecules to move around. And it makes a crystalline structure, but it just so happens that that solid isn't as packed in as tight as you might think. So my analogy for this that I was really proud of is if you had that same dance floor, but instead of letting people move around in it, you put a bunch of chairs in.
Okay.
So if there were seats, and say the seats are all maybe like have 1 square foot of space around them or 3 square feet of space around them or something, there's some space between them. And everyone gets to sit in their seat. So again, they're in their seat. They're not able to stand up and move around a lot. They're fixed in their position, but it's taking up way more space than if they were jam-packed together.
Got it. They've become still.
They're stuck in their seat.
But they aren't packed in as tightly as they would be
if they were all standing up.
Right. Okay.
So if they're all standing up shoulder to shoulder, packed in super tight, then that would be normal solids.
Yes.
But ice solids, they're still kind of stuck where they're at. They're still in a crystalline structure, but they have a lot of empty space around them. They're not using their space well.
Okay.
Much like chairs.
Got it.
In a concert hall.
Right.
You can literally fit less people in a concert hall if they have to sit down instead of stand because they need more space.
Right. Like in a theater.
Yep.
Yeah, versus going to a standing room only place like you said. Okay. Yeah, makes sense.
Exactly. And that's kind of what happens with water is they are very structured, just like other solids. It's very orderly, in fact. And the molecules are held tightly together, but they're held in this arrangement where there's physically empty space between the molecules because of the way they're arranged, just like chairs.
Okay. Interesting.
Okay, so let's talk about what water molecules look like. Okay, so the best way I could think of to describe a water molecule is actually that it looks like Mickey Mouse heads.
Okay.
So there's one big atom, the oxygen, and 2 small atoms, the hydrogens.
Okay.
There's also some lone pairs on the oxygen, which push the 2 hydrogens closer together than they would.
Okay.
So that's why they're kind of at the top of the Mickey Mouse head.
Okay.
And then the extra electrons are almost like where his shoulders would be.
Okay.
So you've got this Mickey Mouse head, and because of the nature of the way that the molecules are bonded together, water is polar. And if you want to learn more about polarity, go all the way back to our very first episode, which is how soap works.
Right.
And we go in depth about the difference between a polar bond, a polar molecule, and what that means. But essentially, it means that there's positive charges permanently on one side of the molecule and negative charges permanently on the other. And in the case of this water molecule, this Mickey Mouse head, the ears are the hydrogens, and those are positive. And then the negative charge is concentrated at the bottom of his head, sort of the bottom of the round part near where a chin would be. Maybe.
Yes.
So when these molecules are forming liquids, they can come near each other, fit in, go away, come together, come apart, and they can actually get pretty close together because they're able to then repel each other with their positive, negative charge, whatever.
Yeah.
But when they're fixed in place, they want to optimize the positive charge being lined up with the negative charge.
Right. Okay.
So what happens is you'll have a Mickey Mouse head with 2 positive ears, and that lines up next to a Mickey Mouse neck where the negative part is.
Got it.
And then you've got another positive part lining up, pointing outwards from that same one. So that lines up to the negative part of another one. So the way that they fit in actually is shaped like a honeycomb, kind of. Where they make these little hexagons with 6 corners because that is the best way for them to pack in close together and line up the ears with the bottom, the positive with the negative, positive with negative.
Yeah.
But it ends up like a honeycomb, leaving a lot of empty space.
Got it. Okay.
So when I visualize the molecular structure of water frozen, I visualize it as a honeycomb, actually, with our water molecules lined up in a hexagon pattern. And we briefly talked about this on our episode also about snowflakes.
Right.
But because it lines up like that, there's a lot more empty space in the solid of water because it has this weird Mickey Mouse shape with a permanent polarity in it. And so the way the intermolecular forces bring them together when they're going to be stuck there permanently, they try to optimize the way that they're stuck on. And so they take up more space than they normally would.
Got it. Interesting.
So I thought of it sort of like if you have a bunch of old people who are tired and they can't really handle standing at a concert for 3 hours, that's when we put chairs in.
Right.
Because you have to optimize their experience in the concert or else they won't come.
Yeah. Or some like concert I've been to, just the vibe of whatever artist or it is, band,
right.
whatever. That's just the places they go. They go to theaters.
Right.
They do shows where everybody has an assigned seat.
Yes.
They don't do standing up.
Exactly.
And then it's like, sorry, there's no other way for this to work.
This is how it has to happen.
This is how it happened. There is going to be lots of space between you.
Yes.
Yeah.
But in water molecules, because when it's in the liquid form, they can move around more. They don't have to be stuck in that. They're like moving close together, coming apart, moving together, close apart. They have all this energy to move around. They don't mind coming together in the least optimal pattern because it's so short-lived.
Right.
But when it's solid, they're fixed in place, so you really have to optimize what's happening.
Right.
So it's like it doesn't super make sense for a dance floor to have chairs on it, right? So when it's in its liquid state and everyone's moving around, great. But if you're going to be sitting and watching a very chill concert for 4 hours, it makes the most sense for there to be chairs.
Right.
And that's what's going on with water.
Okay. Interesting.
So because then that same number of molecules has to line up in this exact same way, there's a lot of empty space. If you have 100 liquid water molecules and 100 solid water molecules, the solid water molecules are physically going to take up more space, even though they weigh the same amount.
Yes.
And so that means because they're taking up more space, they have less weight per volume, which means they'll float on top of water.
Right. They are packed together less densely.
Yep.
But even in the same amount of molecules, there's more space between them. So they are going to float.
Yes.
Above their liquid counterpart.
Yes. They're packed together less densely, but in a way that is more energetically favorable because the positives and negatives are lined up.
Got it.
And there's usually a pretty good visualization of this in textbooks where it just has like 3 squares that are the same space and it has like a few gas molecules and you can tell that they're moving. You know, there's like dash lines around them so you can get the vibe that they're running around crazily. And then there's the liquid water one where the molecules, there's a lot more and they're moving around and they're kind of haphazardly placed. And then you get the solid water molecules where they are very clearly ordered, but also less of them fit in that picture.
Right.
So maybe I can post that on our Instagram or something.
Yeah, that'd be cool. And then also even maybe a drawing of the hexagon thing or whatever.
Oh, yeah.
Might be cool
they
too.
do show it. They show the honeycomb structure.
Part.
Yeah.
Okay.
When they show the water molecule structure, they usually will depict it in that honeycomb structure so you can kind of see the Mickey Mouse heads lining up.
Got it. Dude, cool. Interesting.
I think it's so interesting. I really do think that what's crazy is if you start to think about how the world would be different if water didn't float when it froze. But let's save that.
Yeah.
That's a little treat waiting for us at the end of you teaching it back to me.
Okay, cool. So I think I have an analogy for this.
Is it going to be better than my analogy or worse? Just kidding.
We'll let the listeners decide. So imagine you have a concert hall. What if I like really straight face just totally did the exact analogy?
You couldn't because I could see how excited you were to make that joke leading into you saying it. So I knew that you were about to say something totally
sometimes
ridiculous.
I'm better at hiding it, but I thought about it too long. What helps to keep a straight face if you just think about it right before you say it. If you give yourself any amount of time, that's when it's hard.
It starts to be funnier and funnier to you.
Yeah. But I would love it. Like if I just kept straight face, like super straight delivery, even the listeners are like, isn't that exactly what Melissa just said? That'd be so funny.
I did have a friend. You actually know him, probably Brandon. He would say these. He would make an inside joke and never even look at the person he was like making the joke with. Like he would make an aside as if it was nothing, and he would just like out of the corner of his eye, like see their reaction. But it was like nobody else really knew what was going on.
Nice.
Those
nice
were
and
good.
subtle.
Yeah,
I love that.
Those. Do you have an actual analogy, or were you just only doing it for the joke?
No, I don't. I just want to make that joke. Because honestly, like I think some things that were going through my mind a little bit were just similar enough. Like they didn't actually change the dimension. I was thinking about other things that basically were people in a space, and what things changes the density of the people, like how closely they're packed together or not. And so, I don't have a huge difference. But so let me just explain it back in my own words.
Okay, I think that will help anyway.
Yeah, it'll help me make sure I'm not missing something. So typically with a solid, starting there, it's molecules packed in tightly together with not much room or energy to be able to move around.
Yes.
And they're held together also by molecular forces, intermolecular forces.
Intermolecular forces, yeah. That's what holds everything together.
Right.
Except the individual molecules' bonds aren't intermolecular forces.
And that would be, using some analogy you used, that would be like a very densely packed, I'm going to use that word on purpose, densely packed concert hall where it's standing room only. Everyone is shoulder to shoulder, chest to back, very tightly packed in.
Yes.
Cannot move around.
Yes.
The room is the size it is, and it is a fixed size.
Yep.
And they cannot move.
It's probably a fire hazard to have that many people in there.
It truly is. Honestly, this hypothetical concert hall is asking for a disaster to happen. So then pretend that you're able to suddenly expand the walls, make the space bigger, and people can start.
You push back one of those dividers in the room.
Exactly. Yep. A divider in the room or whatever it is. And the people can start moving around a little bit, dancing. They got a little bit of freedom. And they have a little bit more space to do that.
Yes.
As well. But it's the same number of people, which is why typically a liquid would be less dense than the solid version of itself.
Yes.
Same number of people, same number of molecules.
Yes.
More room to move around, so they are less densely packed together.
Yes.
Which means they float and the solid sinks.
Yes. Like if you had an ice cube that didn't expand and instead contracted like most things do when they freeze, and you drop that in your water, boom, sink straight to the bottom.
Straight to the bottom.
Like other things do when you put them in water.
Yes. But weirdly, water, instead of being like the concert hall that's packed shoulder to shoulder, standing room only, when it becomes solid, it's like everyone gets a chair.
Yep.
And when everyone gets a chair, everyone takes up more room.
Yep.
And that means you need more space. And so water, everyone gets a chair, they all sit down, and then suddenly the same number of people are actually taking up more space than they were a moment ago.
Yes.
And so it's expanded and it has become less dense.
Yes.
And then it floats above the liquid version of itself.
Yes.
Blowing the minds of whoever it was, Aristotle or Galileo, whatever. Who'd you say?
Galileo, I think.
I don't know why I said Aristotle. Whatever.
They had a public debate about it. That was what people used to do for fun. And also, that's kind of what you all are still doing for fun, listeners of Chemistry for Your Life.
True. And not much has changed.
No, that's true. And that article is all about that there's still so much about water we don't understand.
So that is why water, the solid version of water, which we know as ice, affectionately we call it ice, floats.
Yes.
It's taking up more space as a solid.
Yes. The same number of molecules take up more space as a solid, meaning it's less dense.
I guess I should say the reason why is because water is polar, which we've talked about.
Yes, yeah.
And when it's in solid form, it wants to orient itself where the positive end of one water molecule is near the negative end of the other water molecule.
Yes.
Which means they can't just fit in really tightly.
Yes. And it is like each Mickey Mouse ear gets its own new oxygen that it's attached to. So imagine start with one Mickey Mouse ear or one Mickey Mouse head, and each Mickey Mouse ear has the bottom of another Mickey Mouse head. And each of those have two Mickey Mouse heads on top of their ears.
Yeah. So there's always going to be this void in between.
Yep.
Where there's just this room where nothing's there.
Yes.
And we call that void, in chemistry we call that void the eternal abyss.
No, it's empty space.
Yeah, or empty space, whatever. Yeah. Different strokes, different folks.
The eternal abyss.
Yeah. And so
we're recording this late at night, and I definitely have the sleepy time sillies. That's why I'm laughing at Jam's jokes more than usual.
Yes, more than usual. I'll take it. And that's why the polarity of water is a huge factor in this. It's not just, happens for water. Who knows why?
Yes. That's a good point. I'm glad you pointed that out. Yeah.
And did I miss anything?
No, I think you got it. I think that's a really good explanation. And actually, I feel like I was able to explain the Mickey Mouse head arrangement a little bit better this time than I was the first time around. So that helped me too. Your explanation also helped me think about how to talk about it. So that was really good. Awesome. Part of what I like about this analogy is usually what we talk about when we talk about molecules going from the solid to the liquid to the gas phase is putting more energy in them.
Right.
And that's definitely a way to melt a solid, turn it into a liquid, and then turn the liquid into a gas. But what we haven't talked about is the relationship that pressure also plays in that. So you can actually turn a liquid into a solid by applying very high pressure because it forces the molecules closer together.
Right.
And then relieving the pressure will let the solid go back to the liquid.
Right. Okay.
And that is something that plays out in our everyday life in how water is different. Because if you can imagine the ocean, the bottom of the ocean is under so much pressure. And if it was under all that pressure and the solid state was the molecules being really close together, the bottom of the ocean would probably always be frozen from this increase of pressure.
Oh, dude, that's crazy to think about. But because water doesn't work that way, it's the other way around.
Because the water molecules can be closer in their liquid state than they even can in their solid state.
Yeah.
It stays in the liquid state at the bottom of the ocean.
And icebergs float to the top.
Icebergs float to the top. All ice in lakes, when they freeze over in the winter, rivers and stuff, is at the top. So that also is beneficial because underneath that, the aquatic life forms can still exist.
Right.
Ice fishing can still happen because ice floats. And there's still bodies of water underneath where fish and other aquatic life is. It's not frozen down there.
Yeah. Interesting. It's weird to think about that in other situations. The pressure works that way. We're all used to water. So it's one of the most common things that most of us interact with every day.
Yes.
And it's interesting to think that it's an exception to these rules that do apply to so many other elements. And it seems so odd to think like water under a lot of pressure, if it was something else, would become a solid.
Yeah.
Because it seems like, water doesn't, and we know that. So it seems like that's the rule. It's like, no. Actually, water's kind of the one that's breaking these rules here.
Yeah.
But it just also happens to be the most common thing
that we're used to.
Yeah.
Yeah. So sometimes I'll catch myself worrying that other things will expand when I freeze them. And then I remember, wait, no, that's just water. I catch myself kind of like, is this going to take up more space? And then I think, wait, that doesn't make sense.
Yeah.
So I did actually even just Google what if ice was more dense than water, and it was a pretty fun thought experiment just to imagine how it might impact the world. One thing they talked about is how much the water on Earth regulates the heat because it has a high heat capacity and specific heat, which we talked about in the sand and water episode, which we just rebroadcast. So there's so many tiny implications of this that are really fascinating. So I encourage you to just spend some time thinking about all the ways that ice and water acting differently under pressure, acting differently when they freeze might be a positive impact on the world. And then just Google it and see what other things other people came up with.
Yeah.
It's pretty fun.
Interesting.
Well, speaking of fun things, do you want to wrap up our episode this week with something fun that you've been doing recently? I have a good one I'm very excited about.
Yes. So last week, Em and I were able to take our son and go out of town for a few days.
Oh.
And some of my family members, they have a lake house they let us use. And just got to have like a little bit of just like quality family time. Some people call this like a baby moon kind of deal, but whatever. Just like, this is like our last time to do this, just us three, you know? And so we did that.
That's
and just
so cute. Just us three.
Just us three. Just had a really chill 4.5 days out at this lake house. Just got to hang out, eat good food, not have a lot going on.
Yeah.
Get some quality time together. Sort of calm before all the changes of adding another kid to the mix. So we did that, and it was really relaxing. It was really fun, really chill.
Yeah. While you're talking, I was thinking how weird it is that your son right now kind of has no idea what's about to happen.
No idea.
And also that it will never just be you three when your new son is here until your first son goes off to college.
Yep.
And just the different life experiences of a first versus a second child.
Yeah, it was actually the first time I really took time to think about what that change will be like. That there is, you're gaining something, but you're also losing something. It's just how it works.
Yeah.
But I just hadn't thought about that. I hadn't taken time to just think about, there was this period of time, only this little period, where there was only one kid.
Yeah.
And 2 adults. And the next time it happens, it will be when the last kid is left here, but is fully grown and fully an adult and not, about to be leaving or whatever. And it won't be anything the same, you know? It won't be.
And
similar.
Also how much the first child didn't ask for that.
Yeah.
And how much the second child is sort of being born into a world that was built by the first child. The first child's preferences, and they got to do kind of what they wanted because they were the only kid.
Yeah.
And so both parties didn't agree to that, but they just get shoved into it. They couldn't even agree to it because they're so young, you know?
Yeah.
So life just sort of happens to them.
Yeah. And that's why we decided a long time ago, Em and I, that we're not doing a democracy. I don't know exactly what you'd call it, but it's mostly, I think, a monarchy, probably. And so that works best for us. We make those decisions and they just have to, you know.
It's just interesting to think about it, about how much of your life is shaped by these things that you have so little control over.
Yeah. Yeah.
You know, like your first son will always be shaped by the fact that he was an older brother.
Right.
And your second kid will always be shaped by having that older brother in his life and being born into your family after he was there.
Yeah.
You know, it's just interesting.
Yeah.
Interesting to think about.
And it's hard to give any blanket statements for this stuff. But for my own experience, I think I was improved by the fact that I had 2 brothers. I had an older and a younger. I kind of had both experiences of that. And I have come to the opinion that it was best for me. It was good. I learned a lot of good stuff. So,
like most things in life, it might be easier and seem more fun in the moment for you to get to do whatever you want all the time.
Yeah.
Having a sibling really does. It can be more challenging, but I also think it gives you a lot of good life skills.
Yeah.
It's just interesting to think about it from the perspective of, a kid.
Yeah, totally. Yeah.
It's how weird it is that then there's just going to be a new baby and you didn't want that or ask for it.
Yeah.
And now all of a sudden there's a baby that lives in your house with you.
Yeah.
Yeah, it's just funny to think about it like that.
Yeah.
Interesting.
That's what's been happening with me. What about you?
Well, mine's not that cute, but it is also about family.
Nice.
So one of my cousins, my cousin Rachel, decided to throw, I have 2 cousin Rachels now, actually, because I married, oh no, I have 3. I married into a cousin Rachel.
Wow.
And then there's a cousin Rachel on my mom's side and my dad's side. Wow.
Dang.
Okay, so my dad's side of the family, cousin Rachel, threw a family trivia night at a Mexican restaurant.
Nice.
And it was really fun. It was me and my dad, my brother and Mason, and Edison. My brother's son was there too. He was not really contributing to the team, honestly.
Right.
But he was cute.
Yeah.
Comedic relief.
There you go.
And it was really fun. And I thought we were going to do pretty badly because I don't feel like I know a lot. And we won.
Nice.
All of our different strengths played out. So that was cool. Mason has watched a lot of Good Mythical Morning. So he knew the answer to the question of what the first fast food restaurant in the United States was.
Whoa. Interesting.
I know. My dad knows a ton about sports. He knew one of the teams in the first football game ever played between 2 college teams in the United States.
Interesting.
I know, like, what an interest. I'm like, oh, that is never even anything that I would have thought about.
Yeah.
And he had that.
Yeah.
And I knew one about the Wizard of Oz.
Nice.
The color of her shoes. In school, I learned that they changed it to ruby for the books, but it was silver, or for the movies, but it was silver in the books.
Oh, interesting.
So these like random facts that each one of us had, we all got to contribute one of those. My brother knew about alcohol. Gin is made with
juniper berries.
Yes, I never would have known that. Wow,
Yeah.
you knew it off the top of your head. You could have come to our trivia team.
I know a lot of trivia.
Really, I don't.
Won't ever benefit me until I'm at a trivia night. I live hoping there's a trivia night that comes up.
Well,
that's how I live my life.
Well, I'll go to trivia night with you. Our friend does one every Wednesday.
Deal. I do love trivia. So
we used to do trivia at the movie theater. Actually, one of the first times Mason and I ever hung out, it was with our small group doing a trivia night. That was really fun.
That was my favorite because there's so many movie related things, which is definitely plays to my strengths.
Yeah.
Not all of the questions are, but a good amount of them end up being.
Yeah. That was really fun.
Yeah.
So my family won, and that didn't even matter because I had a great time.
Nice.
It was really good. I have been stressed about family get-togethers around holidays, and so it being just kind of a random day in the middle of the summer, and there wasn't a lot of stress going into it, was really, really nice. So
yeah,
shout out to my cousin Rachel for facilitating that. I had a really, really fun time with all my extended family and being on a team with, my immediate family. It was really a fun night.
Dude, that's awesome. Very cool.
So thanks again, Rachel, for doing that. And thanks to all of you listeners for coming and letting me teach you about how and why ice floats in water and how that's kind of weird.
And thank you for teaching us. And yes, it is kind of weird and very cool. And in fact, some might even say it's cold.
Oh, no.
Yeah. And so if you have a question or idea about something that's chemistry related in your everyday life, please reach out to us. We love your ideas, just like Wendy did. Reach out to us with this question. And so you can do that at Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, FOR, Your Life, to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to ko-fi.com/chem4yourlife or tap the link in our show notes to donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing on your favorite podcast app and rating and writing a review in Apple Podcasts. That also helps us share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode can be found in our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to A. Molina, who reviewed this episode.